Hi, thank you for joining the, I think this is the third installment of lecture videos for the, for chapter 2. And last time we talked about different types of reaction mechanisms or different types of reactions that happen often with organic reactions. And of course, sometimes it might be hard for you to see how things might get categorized into those four, and then it's not like nature agreed with us that those are the only four types of transformations that molecules undergo. So some things don't quite fit in there, but these are sort of the most commonly seen type reaction types. And one of those actually is an acid-base chemistry, but we kind of separated that as its own sort of subsection because it's really common, but also it kind of deserves its own treatment. So you could just think of acid-base chemistry reaction or reaction step as one of these categories, like perhaps the fifth category of reactions. Okay, and this is something we see very often. So I would maybe see the proton transfer is perhaps the most common reaction mechanism step. And I call that a step because particular reaction mechanism, meaning like a particular reaction, how it happens, might involve multiple steps. Maybe the first step is exchange or transfer of proton, and then followed up by addition reaction or something like that. So, okay. Anyway, this is just mostly review of general chemistry, hopefully, but this right here, let me get to a pointer, it is sort of how a acid-base reaction is can be depicted in a generic sense, right? This just shows this acid HA lost its proton to become A minus, and hopefully you kind of remember the terminology because it's always hard, kind of a bummer to have to memorize or learn a new terminology or vocabulary, but it's kind of important just because those are the words, the concepts we use to describe more complex concepts, right, in science. So this would be the acid. How do I know? Because it's losing a proton in the course of this reaction. And this, we would call that the conjugate base. And I want you to see that in this case, water here is picking up a proton. For that reason, this is acting as a base. So let's just designate that real quick. So this is our acid. This is our base. Now, that doesn't mean that water is always going to act as a base. Sometimes it can act as a proton source or acid if the if it's reacting with a strong base, right? So it just all depends on the acidity or basicity of the other thing that it's reacting with. And then this would be called the conjugate base. And the reason why it's called a base is because in the opposite direction, this is reversible, A minus would pick up a proton to become HA. So it's in the other direction, it's acting as a base, and it's conjugate base because it's the sort of the reaction pair with this acid molecule. It's just the base that's resulting from losing a proton from the acid state. That's called the conjugate base. And then any guess as to what this might be called? Well, that would be the conjugate acid, because in the other direction, it would act as an acid, and it resulted from the base picking up a proton. Okay. All right. And hopefully you also remember the discussion about pKa, where P just means negative log of something. Like pH is a negative log of concentration of proton. And then Ka, if you recall, is the equilibrium constant for this acid reaction, right? And it's remember, equilibrium constants are defined like product over reactant. So the product here in this case is A minus the conjugate base concentration times the conjugate acid. Those are the two products, and the product, the reactant is Ha. Now, technically, water is also a reactant, but usually if you're assuming this reaction happens in an aqueous environment or in a water solution, basically the whole thing is water, right? Like the solution is basically most of it, 99.9% of it is water, and so it just remains constant even if a little bit of it is consumed to become conjugate acid. The whole thing is not going to be replaced by that. And so for that reason, the water concentration per se kind of stays the same. I hope that makes sense to you, right? Like it's just so large compared to the little bit of solute dissolved in it that it's essentially a constant, and that's why you could not put this in there, because this is a constant. So this constant H2O concentration is kind of calculated into this Ka constant. I hope that makes sense. Now, this also can be expressed like this, right? On the left here, what I did is I just did the dissociation of the acid, and we can kind of think about that separately from the picking up of the acid by the water. And so that's going to be picking up of the acid by the water would be the product. These would be the reactants. And of course, this part can get canceled, and hence this becomes that equation, because water here is basically a constant, right? So hopefully that's a good review for you. And in terms of mechanistic depiction of this, often like we would show this like so with the curved arrows. Remember, every reaction basically is just movement of electrons to rearrange bonds. That's what a chemical reaction really is. So we should be able to explain what goes on in a reaction mechanism or in a reaction by drawing curved arrows to show the electron movement. And what maybe I should write the reaction first. If water picks up a proton, that's what you get. This is, remember, called hydronium ion. And here's the conjugate base of HCl. Right, this is conjugate acid. This is the conjugate base. So hope that makes sense. And then to get there, what we need to show to explain how these reactants become these products is the water using one of the lone pairs of electrons grabbed a proton, right? Proton is partially positively charged in this hydrochloric acid. So that would happen. And then we're breaking this bond, H and Cl bond, and the electrons are moving towards the electronegative chlorine. And that's why it becomes chloride, right? At this point, I want you to see, if I draw all the lone pairs, it's gaining a new lone pair and hence becomes negatively charged. The oxygen, on the other hand, it's kind of losing more control over electrons because it had to use exclusively owned lone pair electrons to form this new OH bond. That's where these two electrons ended up at. So that's what this arrow shows, is this became a bond. Okay, so hopefully that makes sense. And this is the direction of the reaction. How do you know? Because the pKa of this guy is around -6, and the pKa of this guy is around -1.7. They're both kind of a strong acid, but let's think about this. Remember, the pKa, the lower the stronger the acid, right? Why is that? Because the more the acid dissociates like this, that means it's a strong acid. So if the top of this equation is bigger, it's a stronger acid. It's more willing to give up its proton. And because pKa is a negative log, the bigger this number is, Ka, the smaller the pKa. So this is the stronger acid than the hydronium ion. I hope you could tell that from the pKa. Right. So what does that mean? The left side of the equation wants to become the right side more, right? Because this is the stronger acid than that. If this was stronger, the equilibrium would lie more towards the left. But because this is the stronger acid, in reality, equilibrium lies more toward the right. Hope that explanation makes sense to you. So maybe we'll say so the reaction equation arrow could have been shown kind of like this. Okay. Another way of saying it is like that. HCl is stronger. Okay. Now, that's quantitative way of sort of thinking about acid-base chemistry steps, acid-base reaction steps. But sometimes that information is not always available, like the pKa of every species. And in organic chemistry, you're going to have to be able to tell whether a reaction goes to the right or to the left to predict what the outcome of a reaction might be. And so for that reason, we need to have some method or a way of thinking about evaluating relative acid strength by looking at the structure, right? So how do we do that? What if you don't have the pKa value? How do you know which side of the equation is favored in this equilibrium, right? Like between the base and the conjugate acid and so forth, right? Between this side of the equation, maybe I don't need to write that here for now. So to do that, what we need to do is to compare the stability of the conjugate base and the base, which maybe it's obvious, but that's the base in this equation, and this is the conjugate base. And the reason why we need to do that is because, right, if let's say that this is the stronger base than that base, then what do you think happens? Which way would the reaction lean toward? Well, if this is the stronger base, that means this wants to pick up a proton more than this guy. So if this picks up a proton, it becomes that. Oh, I labeled the conjugate base wrong. Sorry. Conjugate base is over here. right? If this picks up a proton, it becomes that conjugate acid, so the reaction would lean towards the right. And if this conjugate base of the acid, if this guy picks up a proton, it becomes HA, so the reaction would lean more toward the left. So if we can figure out which of these two is more stable or more reactive, conversely, then we could figure out which way the reaction is leaning towards. Hope that makes sense. To evaluate the stability of anything, you can use the CARI method, and this really deserves underlining and great emphasis. This helps you evaluate relative stability. Okay, so how does that work? What is the CARI rules? And this is probably one of the most important things you're going to learn in this chapter, but it's an acronym. C stands for charge, and as in charge is bad. Okay, and what does that mean? For instance, right, like let's say we had this reaction equation. That, by the way, is methane. Here's ammonia is losing, according to this equation, a proton, and the ammonia is picking up a proton. And then you might not think anything of this reaction equation, because you might know that ammonia is a basic compound from Chem, so you might not be surprised, you might think this is just normal that it's picking up a proton, but would this be a reasonable reaction? Well, the answer is it's really not, mainly because this is a much weaker base than this very unstable and reactive carbanion base, which is really, really strong. And so for that reason, the reaction equation lies far to the left. In fact, it doesn't really go at all. One of the ways we could pick up on that, without knowing this, the pKb of this base versus that base, is this guy has a negative charge, whereas this doesn't. So this is much more unstable or reactive, right? Maybe I'll write that here. Right, that's what you can glean from the C rule, the charge rule. Okay, the A stands for atom. What does that mean? That's the atom that has the charge on it. And what this rule means is you have to consider the electronegativity. And polarizability to some extent. Some atoms are more polarizable than other atoms. For instance, NH4 with a positive charge on nitrogen is more stable than the hydronium ion with a positive charge on oxygen. Why is that? Well, oxygen is more electronegative. Oops. Right. So that's kind of the stuff we mean. Another combination we could think of, we could compare hydroxide ion versus an amide ion, or anion, where the negative charge is on the nitrogen. Well, hydroxide is more stable than amide anion. Why is that? Well, again, because oxygen is more electronegative than nitrogen. So if you're going to have a negative charge, it's better that it's on an oxygen, which wants electrons more than a nitrogen, which doesn't want the electrons as badly as oxygen. Because remember, what confers the negative charges? The electrons. And because oxygen is more electronegative, it's worse to put a positive charge on oxygen than on nitrogen. I hope that makes sense. And another thing to consider, or example where this atom rule comes into play, is the hybridization of the atom. And for now, we could think of it as like the s orbital is more electronegative. That's technically not the most correct way to think about it, but I'll let future physical chemistry classes correct that notion or make it more accurate. And for now, the easiest way to think about it is, remember, s orbital is smaller than p orbital. It's just a tiny sphere, and so when when something is more s hybridized, everything is closer to the nucleus, where there's a positive charge. So if you're closer to the positive charge, right, like from the electron's perspective, it feels like that atom is more electronegative. It wants more electrons. And so for that reason, sp3 is not very electronegative, and sp2 is more, and sp is much more electronegative. Okay, that just means, for instance, if you compare this anion to this anion, where the this carbon, if you draw out the Lewis structure, I hope you can notice that it's sp3 hybridized, whereas this is sp hybridized, and so therefore this is more stable. Okay, so you have to think about the hybridization of the atom. The last thing you want to think about in terms of the atom rule is, bigger the atom, maybe I'll just maybe a better way to say it is, bigger atoms stabilize the charge better. And that's because they're more polarizable. Okay, so for instance, if you compare the alkoxide versus this thiolate anion, the thiolate anion is much more stable because the negative charge on sulfur is more stable than oxygen, because sulfur is so much bigger than oxygen that it's like if there's a little bit of charge imbalance, right, like it doesn't really affect much. It's kind of like if you're gonna give a poison to somebody, it's better that an adult takes it than a baby, because a baby is tiny. It's a little bit of poison is going to affect it much more. It's kind of like that, right? Hope that makes sense. And then the R in the CARI rule, hope I have enough space here, is resonance. Okay, and this just means that it stabilizes. If you have resonance stabilizes charges through delocalized pi system. Okay. So for instance, if you compare this carbocation, where you have a positive charge on this carbon, right? As opposed to this would be called allylic cation, where the charge is on next to this olefin or alkene. This is much more stable, and the reason is this thing has resonance. Like you could move the charge to this carbon, so these two carbons are sharing the charge together through delocalization of electrons. We might depict that like this. These pi electrons can move, and so for that reason this this cation is much more stable. Okay, and then the last thing in the CARI rule is I, which stands for inductive effect. What does that mean? This means that this happens through stabilization or conversely, you could think of it as destabilization through the sigma system. That just means like through a regular single bond. What does that mean? Inductive effect just means because of the difference in electronegativity, a particular atom might pull electrons toward it more than the others. What do we mean by that? For instance, if you compare this anion, carbanion, versus this carbanion, right? There's some difference because fluorine is much more electronegative than the hydrogen that's here, and so for that reason these guys are pulling electrons toward it through the sigma bond, these single bonds, and so for that reason this carbon over here is experiencing less of a negative charge than this guy does, and so for that reason this to the right is more stable. Now conversely, if we were comparing the positive charge here and positive charge here, I hope it makes sense to you that this would be less stable because positive charge is made worse by electron pulling fluorine through the inductive effect. So if we're comparing cations, this would be less stable than that, for example. Okay, if there's any questions, if something didn't quite make sense, let's discuss it in class. All right, see you then.